In this lecture, I will introduce Zener diode. Zener diode is a special diode and it is widely used in voltage regulation to maintain a constant voltage across a varying load. It is widely used in voltage regulation. If we want a constant voltage across a varying load, we use Zener diode for this purpose. Let's say RL is the varying load. RL is the varying load. I will connect Zener diode like this. This is the symbol of Zener diode, and if this Zener diode is reverse biased, then we can replace the Zener diode by a constant voltage source, and the voltage is equal to Vz, and this voltage is given in the specification sheet of the Zener diode. We have different voltages for different Zener diode. This is the varying load RL, and we can have the varying current with constant voltage. So the Zener diode is used for voltage regulation. Before moving to the equivalent circuits of Zener diode, I will explain two types of breakdown. The first one is avalanche breakdown. The second one is Zener breakdown. In case of avalanche breakdown, we apply a high reverse bias potential across the diode. The electrons gain high kinetic energy and break the covalent bond, and they also free more electrons due to the collisions, and we have a chain reaction, and because of this large current is produced. The avalanche breakdown occurs in lightly doped diodes. Lightly doped diodes are the normal diodes. Zener diodes are highly doped diodes, and in case of lightly doped diodes, when you apply high reverse bias potential, the electrons will gain the kinetic energy and they'll break the covalent bond and collide with other electrons. This process will free more electrons and we have a chain reaction, and because of this large current is produced. But in case of Zener breakdown, we can achieve the breakdown much earlier. Let me write this down. Breakdown is achieved much earlier in case of Zener diode, and this is because we increase the doping level on both the sides. On N side and P side we increase the doping levels, and we have the breakdown earlier as compared to the normal diodes. In case of Zener breakdown is initiated by direct rupture of covalent bonds. By direct rupture of covalent bonds, I mean tearing of covalent bonds. This means tearing of covalent bonds, and this happens due to strong electric field at the junction developed by high reverse bias potential. So there is difference between avalanche breakdown and Zener breakdown. In case of avalanche breakdown, electrons gain the high kinetic energy and they break the covalent bonds. On the other hand, in case of Zener breakdown, there is direct rupture of covalent bonds because of high electric field. I hope avalanche and Zener breakdowns are now clear to you. Now we will move to the next point, the power dissipation capability. Zener diodes are special diodes whose power dissipation capabilities are much more than the normal diode, and because of this they can easily work in breakdown region. So Zener diodes have high power dissipation capabilities as compared to the normal diodes. When we use the normal diode in reverse bias condition, their properties will degrade. But on the other hand, if we use the Zener diode in reverse bias condition, the properties will not degrade. Zener diode in forward bias region is similar to the normal diode in forward bias region. So this is very important point, because most of the people relate Zener diode to the reverse bias condition only, but Zener diode can easily be used in forward bias region also. There is no difference between the Zener diode and normal diode in case of forward bias region. We can also use Zener diode in forward bias region. It will have similar characteristics as normal diode. This is one important point. The most important use of Zener diode is voltage regulation, and Zener diode acts as voltage regulator when we operate it in reverse bias region, but we can easily operate Zener diode as normal diodes in forward bias region. Now we will move to the next point, that is the symbol of Zener diode. The symbol of Zener diode. First we have to make the symbol of normal diode. This is the symbol of normal diode, P side, N side, and after this I will make crooked N, the crooked N like this, and this is the symbol of Zener diode. The voltage is represented by V subscript Z. This is the Zener voltage. Now I will try to obtain the equivalent models for Zener diode using the VI characteristics of Zener diode. This is the forward bias region and this is the reverse bias region. In case of forward bias region, I have already explained the Zener diode is similar to the normal diode. This is the symbol of Zener diode. I will connect P side to the positive terminal and N side to the negative terminal. Now the Zener diode is forward biased, and I can replace this symbol by the barrier potential 0.7 volts for silicon, and the diode resistance R Z. This is positive, negative, and if we consider RZ to be very small, we can have the equivalent model like this in case of forward bias region. Very simple. Now we will move to the reverse bias region, and I will consider this region from here to here, and this is the region when there is no breakdown. This is the region before the breakdown, and in this region also the Zener diode will act as the normal diode. And I will try to obtain the equivalent model. This is plus, this is minus, because we have to reverse bias the diode. N side is connected to the positive terminal and the P side is connected to the negative terminal. And when this happens, the current through the diode is very small, and when current is very small, we replace the diode with high resistance and we can consider it as open circuit. So this is the equivalent model for the region before the breakdown. Now we will move to the most important part of this lecture. We will try to obtain the equivalent model of the Zener diode when there is breakdown. This voltage is VZK. VZK is the voltage after which the breakdown occurs. Then we have another voltage VZ0. We can obtain VZ0 if we extend this linear region. This will cut the voltage axis at this point, and this voltage is VZ0. And let's take a random point on this linear region, and the corresponding current is IZ. The corresponding voltage is VZ, and this current here is IZK. This is the knee current. Now we have everything to obtain the equivalent model of Zener diode in this region. I will first draw the symbol. We have to reverse bias the diode, so I will connect this side to the positive terminal and this side to the negative terminal. Then we have the potential VZ0 plus minus, and then we have the resistance of diode RZ, and this is equal to VZ. VZ is simply equal to VZ0 plus this voltage, and this voltage is equal to RZ multiplied by IZ, the resistance of the Zener diode and the current flowing through the diode. So we have VZ0 plus IZ RZ, and if you want to calculate the value of RZ, then it is equal to 1 by slope of the curve, and we can easily obtain the Zener voltage if we have these values. If we consider RZ to be very small, then we have the model like this: plus minus VZ0, and this is Vz. So Vz is equal to Vz naught if we neglect the diode resistance Rz, and this is the equivalent model of the Zener diode, and this is very important. Here you can clearly see this is Vz naught. Here you can clearly see the Zener voltage is equal to Vz naught, and Vz naught is already mentioned in the specification sheet. So if you need 5 volts or 6 volts of constant voltage across any resistance, then you can easily connect the Zener diode across the resistance, and if we apply reverse bias potential across this diode, we have 5 volts or 6 volts across the resistance, because you can see Vz is equal to Vz naught, a constant voltage, and we can say that the Zener diode is acting as a voltage regulator. Vz and power dissipation is mentioned in the data sheet. They are mentioned in the data sheet, and these two values are the most important values, and you must have to consider them before any use. And if we draw the diagram for normal diode and Zener diode, then you can see the difference in the depletion layer. This is the depletion layer of normal diode. This is P side, this is N side, and this is the depletion layer. And in case of Zener diode, the depletion layer is much narrow. This is the depletion layer. This is the depletion layer in case of Zener diode, and this depletion layer is narrow if you compare the depletion layer in case of normal diode. I will quickly revise the equivalent model of Zener diode. First thing we have to do is to connect the N side of the diode, to the positive terminal, and the P side of the diode to the negative terminal, so that the diode is reverse biased. And once the diode is reverse biased, we have the equivalent model like this. This voltage is Vz naught, Rz is the resistance, and if we neglect Rz, then we only have Vz naught as the value of Zener voltage. In this case, Vz is equal to Vz naught plus the current is Iz Rz. This is the value of Vz. In this symbol also I will represent the current Iz. This is the direction of the current Iz, because this is the reverse bias current. And in this case, when we neglect the Rz, Vz is simply equal to Vz naught. In numerical problems, we are going to use this model. This model is mostly used. We neglect Rz and we have Vz naught as the value of Vz. This is very important model, because in most of the numerical problems you have to use this. So it is better if you draw this model somewhere, and you must also know how to obtain the models using the VI characteristics. This is all for this lecture. See you in the next one.